So, we are going to move to the next topic, this flow past cylinders. Now, flow past cylinders is actually much more common than flow past a flat plate. So, for example, if you look at the humidifying towers, there is a humidifying tower behind the library. So, if you look at the humidifying tower, there are tubes which are going inside, and so there will be fluid which is flowing past these tubes. If you look at heat exchangers, most of you have visited these RCF, right? So, you must have seen these heat exchangers. There are these shell and tube heat exchangers. So, where you have in shell and tube heat exchangers, the typical sketch of that is you have an inlet stream, so you have two fluids, okay. Fluid 1 is actually going through the tube, so that's the tube, so this is called the tube, and this is called the shell. That's why it's called shell and tube heat exchanger. So you see a tube, one of the fluid is flowing through the tube, and there's another fluid which is flowing through the shell side, okay. Now, it could be that fluid 1 is a hot fluid and fluid 2 is a cold fluid. So there is heat exchange between fluid 1 and fluid 2 as it goes through this shell and tube heat exchanger. So therefore, you can see the fluid 2 is actually flowing past these circular geometries, and so it's important to understand how to find heat transport coefficient when a fluid is actually flowing past a circular object or a cylinder, okay. So that's what we are going to see in rest of today's and the next lecture. So the real direct application is heat exchangers. That's the direct application of flow past cylinders. So suppose I take a cross section. I take a cross section of the cylinder, any cross section, and let's say that there is fluid which is flowing past this cylinder, okay. Let's say V is the upstream velocity, which is the velocity very far away from the cylinder. So here's a cylinder which is actually going inside to outside of the board, and this is the cross section, and you have a fluid which is flowing at a certain upstream velocity, where V is the velocity which is very far away from the cylinder, okay. And let us assume that the temperature of the fluid is T infinity, okay. So let's say that this is the, let's say I call this as x equal to 0, a location x equal to 0, and I define my coordinates x as the curved surface location, okay. I can always do that, okay. So now x really goes from 0 to pi r. 2 pi r is the circumference, and so pi r is the distance going from this end to this end, okay. And it's symmetric, so if I know what's happening on the other side, I can easily find out what's happening on the lower bottom of the circle. So it's a symmetric system, axis symmetric system, okay. And now what will be the velocity of the fluid at x equal to 0? So the fluid actually comes to rest okay. In fact, if you look at the profiles, you will see that the fluid actually never reaches this position x equal to 0, because they are actually going past this cylinder. So this is the fluid is actually taking this path, right. So really the fluid is never going to encounter this location x equal to 0. is never going to experience that location, or rather the cylinder is never going to experience the fluid at that location x equal to 0. Okay. Now, if you look at the fluid which is flowing well past this cylinder, okay, they are not in direct contact with the cylinder at all. The only way it feels the presence of the cylinder is because of the deceleration that the fluid experiences because of the presence of the cylinder far away. Okay. So now, suppose I zoom up the upper half of the cylinder, okay, and we have fluid which is flowing past this upper half. Now, what happens to the velocity? If I want to know what is the velocity of the fluid at that location compared to the velocity of the fluid which is flowing well above the cylinder, which one will be higher? Well above or well below? So remember, supposing I take a fluid stream which is flowing in this location, okay. Now, the distance that it has to travel, supposing I mark this as some location Z1 and I mark this as some other location Z2, okay. So, the distance that the fluid travels, the fluid stream which is present well above the cylinder, the distance it travels to reach Z2 is actually smaller than the distance that the fluid particles which is present at this location, although they would have started at the same plane, right. So, if you look at very far away upstream, all of these particles would have actually started at the same time. So, the distance that the fluid stream well above covers in order to reach the same plane is much smaller than these fluid particles that has to reach this location. So, therefore, the fluid particles which is present close to the cylinder or which is experiencing the presence of the cylinder, they have to accelerate in order to catch up. Supposing if it is a steady state. Suppose you have a steady flow, okay. Okay. Supposing you have a steady flow where the volume of the fluid that you are actually pumping past the cylinder is constant. So, whatever fluid particle that has started at this location, they have to catch up before they leave the cylinder. So, in order for it to catch up, these fluid particles, they have to accelerate and they have to catch up with these fluid particles which is flowing well above the cylinder. Same thing can be said for? Yeah. But the distance traveled is the same. So remember that the fluid particles in a flat plate, the distance traveled is the same. There the velocity, there the velocity difference that you see in a flat plate is because of the friction that is experienced by the flat plate. Friction that the fluid experiences because of the presence of the flat plate, and you will see the same thing here in a short while. But supposing even if you have a friction, even if you have this cylinder, in order for the fluid to leave at the same time, they have to catch up. But that's not true in a flat plate. In flat plate, what happens is that the momentum which is present before the experience of the flat plate is distributed because the fluid particles are now moving in both x and y direction. If you have fluid which is moving only in the x direction before the plate is experienced, but in the boundary layer, because of the presence of the flat plate, it's moving in both directions, but the effective mass flow is the same. Unlike in cylinder, what happens is that if you want to have same mass flow rate or the same fluid particles which started at some location and they have to cross the location at the same point, then these fluid particles which is traveling at a larger distance, they have to accelerate in order to catch up. So therefore, if you look at the pressure gradient, so note that here x coordinate is the curvilinear coordinate, not the linear coordinates, okay. So x direction is the it's the location on the along the curved surface, and so dP by dx along the curved surface, that has to be less than 0 in order for the fluid to accelerate. Okay. Now that's not true everywhere. This happens only till a certain location. So what happens is that the fluid particles will accelerate, and the momentum that it carries will actually accelerate up to a certain location, and at some point it's not able to manage, depending upon the upstream velocity, whatever is the magnitude of the upstream velocity, it's not able to catch up with the speed that it has to, and so what happens is that the pressure gradient will go to 0. So at some location, so let's say at this location, it's not always at this location, so let's say at some location the pressure gradient will go to 0. Okay. So that results in the maximum velocity. So there will be this corresponds to the maximum velocity along the curved surface. So remember that the distance that it travels along this location, okay, now because the distance is much larger, the fluid particle has to accelerate. But then when it leaves the cylinder, when the fluid particle leaves the cylinder, it cannot have any acceleration, because it's now going to, it's traveling the same distance as that of the other fluid stream after the fluid has left the cylinder. So therefore there has to be a location where the fluid particles are decelerated, so that the increase in the velocity in order to catch up must be decelerated so that it reaches the same velocity as that of the upstream, as that of the free stream fluid. Otherwise there is going to be a relative motion between the fluid, and so you cannot have a steady flow. So therefore after the location where the maximum velocity occurs, there will be a deceleration of the fluid, and so you will experience a situation where there is an adverse pressure gradient. This results in the deceleration of the fluid. This results in the deceleration of the fluid particles, and this results in the acceleration of the fluid particles. So remember that the location where you get a maximum velocity, where the pressure gradient goes to 0, that depends upon the upstream velocity. It's not true that the location where you have dP by dx is 0 or a maximum velocity, it occurs only at one location. So it completely depends upon the upstream velocity and how much it's able to bear the acceleration of the fluid. Okay. So now at some location what happens is that the fluid is now decelerated, but then it's decelerated to a certain extent that the velocity would come to 0. Okay. So the deceleration is so much that at a certain location, what happens is that the fluid particles is no more able to sustain the adverse pressure gradient, and therefore the fluid particles will come to rest. Now what happens when it comes to rest? It's not able to move further. When the fluid particle comes to rest, when the velocity is 0, it's not able to move further anymore, and so it separates out from the cylinder. So this point is called the separation point. So the fluid is no more able to move forward because the adverse pressure gradient is so much that the velocity comes to 0. The moment it comes to 0, it separates out from the cylinder. It's not able to move past the cylinder anymore because the adverse pressure gradient is so much that it's not able to manage to move past the cylinder. Now once it separates out, once it reaches the separation point, So this is the separation point where the velocity of the fluid stream at the interface is 0. Now once it separates out, the pressure gradient has not changed. The pressure gradient is still adverse pressure gradient, while the fluid particles above are moving forward. So in order to keep up with the adverse pressure gradient, what the particles will do is they will start moving in the backward direction. So you will start having a profile, a velocity profile, where the fluid which is close to the cylinder. So note that this is at the leading edge of the cylinder. Okay, it's not at the lagging edge, it's at the leading edge, where the fluid particles now very close to the surface will start moving in the reverse direction, because it's not able to sustain the adverse pressure gradient, and some of these particles will start moving which is far away from the surface will continue to move in the forward direction. So you will have some particles which is moving in the reverse direction or the backward direction, and some fluid particles which is moving in the forward direction. So if this continues, then what happens is the circulation of these fluid particles. So this leads to what's called the wake formation or internal circulation of fluid particles in the local region. So this is called the wake formation. Okay. So there is a series of interesting events that actually occur to these fluid particles which is flowing past the cylinder. So it first experiences an acceleration, and then it's not able to sustain the acceleration, so the velocity goes to a maximum and starts falling down, and there's an adverse pressure gradient in order to catch up with the rest of the fluid stream, and it's not able to manage the adverse pressure gradient, and therefore the velocity comes to 0, and so it leaves the surface and then it starts circulating in the cylinder. Okay. So that's exactly what happens in this location here. So what you will see in this location is that the fluid particles will start rotating, and there will be wake formation, similar to what you would see in a turbulent flow where you have constant mixing and circulation of fluid. You will see that in all the hydrodynamic conditions, both laminar and turbulent conditions, when there is flow past cylinders. Okay. Now the only difference between laminar flow and turbulent flow here is that the location where the separation occurs. So the separation point for laminar flow is less than 90 degrees. So if I call this as my theta, for laminar conditions, once again it's defined by the Reynolds number. So here the Reynolds number is defined based on the diameter of the cylinder. If d is the diameter of the cylinder, so Reynolds number is defined based on the diameter of the cylinder. So if this is less than 2 into 10 power 5, this is less than 2 into 10 power 5, it's considered as laminar conditions, and under laminar conditions the separation point is approximately at 80 degree angle. Okay. So it's somewhere in the 80 degree angle in the laminar conditions, while under turbulent conditions, I can write it here, under turbulent conditions the angle of separation is about 140 degrees. Okay. Oops, that's not a C, not temperature, sorry. So the angle of separation, the separation point occurs at 80 degree angle when it is laminar condition, while it is turbulent condition it occurs at 140 degrees. So this is interesting because the wake formation that you would observe in laminar conditions, you will start seeing wake formations right next to the cylinder for a pretty good distance when the fluid is flowing past the cylinder. While under turbulent conditions, you will see that the wake formation is only towards the leading edge of the cylinder and not very close to the top surface. So this is a very different phenomena compared to what you see in a flat plate case, where you will never see a wake formation in the laminar conditions, while you will see recirculation of fluid even under laminar conditions when the fluid is flowing past the cylinder, and that's because of the geometry. So the hydrodynamic conditions, boundary layer. Okay, similar to friction coefficient. So here what you have is called the drag coefficient. It's very similar to the friction coefficient that was defined earlier. So it's called CD, and that's given by the drag force divided by AF rho V square by 2. So AF is the surface area of the front side of the cylinder. Okay, so this is the frontal area, that's the front curved surface of the cylinder. So that based on that the drag coefficient is defined, and if I look at the drag coefficient as a function of Reynolds number, so you will have a slightly decreasing, it's a decreasing function, and the reason is very simple. So remember that when you have laminar conditions, the separation occurs at a much smaller angle, and there because the drag is much higher, and at turbulent conditions because the velocity is much higher, the drag is not that high, and therefore the drag coefficient is much smaller. And so I can put some numbers here. So this is 10 power minus 1, it's a log plot. 10 power 1, it's about 10 power 6, and this goes from 0.06 to 60. Okay, so that's the profile for drag coefficient. So when the boundary layer analysis, which we will not do in this class, so the boundary layer analysis suggested that the Nusselt number, that's defined now based on the diameter of the cylinder. So this is given by H into D by Kf, defined based on the diameter of the cylinder. So that's now some function of the power of half and Prandtl number to the power of 1 by 3. So that's again based on the boundary layer analysis, and so there's been empirical correlations which is available for this problem. So there are no clean theoretical predictions which is available. So one has to rely on the empirical correlations which has been observed by performing repeatedly several experiments. And so the empirical correlation is (1 by 3), and so if C is Reynolds number 9, M is 0.33, and for between 4 and 40 C is 0.911 and M is 0.385. So that's the correlation that's available for Nusselt number. And so a general correlation is called the Churchill-Bernstein correlation, which is useful for estimating the heat and mass transport coefficient for flow path cylinders. So that's given by so note that it's a correlation based on experiments. So the best you can get is the average Nusselt number. You will not be able to find the local quantities anymore. Plus 0.62 Re 3, 1 plus 0.4 by 4 2 0. So you will start seeing all kinds of correlations, because one cannot get analytical solutions for some of these problems, and one cannot even get approximate analytical solutions. So even numerical solutions becomes very non-formidable, and so one has to resort to these kinds of correlations. And note that these kinds of correlations do not always give a very good prediction. I would say that the error is somewhere between 5 and 10%. Again, this has been verified for some experimental conditions, so there is always some error in the prediction of the heat and the mass transport coefficient. Of course, because we know that the boundary layers are similar, one could always replace. So if you want to get mass transport coefficient, so you simply replace the Nusselt number with the corresponding Sherwood number and Prandtl number with the corresponding Schmidt number. So you get the correlations for the mass transport problem. So there is no point in rewriting it for mass transport, except that you have to just replace Nusselt number with Sherwood and Prandtl number with Schmidt number.